Hi, everyone. Welcome to our interim presentation on the analysis and redesign of an automatic vegetable peeler. We're Team 8. Our team members are Lucas Hissong, Aditya Dutta, Esben Nielsen, David Buck, Patrick Wren, and Harsh Shah. So a bit about our product is the automatic vegetable peeler is used to remove the skin and peel of an assortment of vegetables like potatoes, onions, and carrots in an efficient and non-wasteful way. The vegetable is attached to the sharp lower grip, which is spun by a motor, and a sharp upper grip, which is free to spin about the vertical axis, which is how the vegetable is rotated. The blades are placed on opposite corners of the vertical shafts, and they lightly engage the vegetable surface, and they're moved up and down by another motor, and this is how the entirety of the vegetable will be peeled. Based on our preliminary market analysis, the production volume is estimated to be around 50,000 to 200,000 units per year. We've gone ahead and identified two different target customer groups. The first, the primary being commercial kitchens or manufacturing plants, where it's necessary to peel large amounts of food in an efficient manner, either to serve a large amount of customers or mass manufacture foods. Our secondary market will be personal kitchens, where the convenience of monocross is desired, but it is not necessary to peel a large amount of foods to serve a specific customer.
We've broken down our model of the peeler into 18 individual parts and subassemblies, each labeled and with the required quantity needed for our system provided. On the right-hand side is an image of an exploded view of our CAD model with callouts for each part and subassembly, which are circled in red.
This is our FAST diagram, which shows the main function of this product, which is peeling vegetables, split up into more detailed functions to the right, and better characterizes the behavior of this product in more specificity.
Here we have got two assembly sequences with the fishbone diagrams. And both of the sequences, we start from the down plate. The first sequence focuses on building the assembly by attaching the individual parts and increasing Z direction. The second sequence focuses on attaching sub-assemblies and then putting them together. Comparing both the sequences, assembly sequence 1 would be easy to assemble with smaller parts as we have got individual parts to assemble and then attach it to the main frame. Whereas in assembly 2, we have got different sub-assemblies and then we attach it to the main assembly. So we have got assembly sequence 1 with higher points than the assembly sequence 2. Hence, assembly sequence 1 is preferred.
This is our function component mapping matrix with the functions in the first row and the components in the first column. As you can see from this, the function provide structure has the most associated components with the base plate, pillar, side plate, and some of the slider supports and stepper motor mounts. With this, you can see that this is the prime candidate for optimization.
Here's our bill of materials, which includes all of the manufactured parts and some of our purchase parts, and most of all of our purchase parts as well. And for each of these, we've estimated material cost, processing cost, assembly cost, and tooling cost based on industry standard. And so we've come up with a total cost of assembly and manufacturing as $909.64 for the vegetable peeler. And so we've gone ahead and done a quad chart classification of all these parts in the bill of materials. And so in our high cost, low importance category, we're looking to optimize the cost of these parts. In the high cost, high importance category, all of these are purchase parts except for the slider plate. So we're looking to optimize the slider plate for cost. And then in the low cost, low importance category, we're looking to consolidate or completely eliminate these parts as they are mostly unnecessary.
This is our functional differentiation table, which shows that the functions that are different between our two customer groups are detecting the size, gripping the vegetable, preventing cuts, and controlling rotational speed. These correspond to the top pillar, end grabber, and slider assembly modules in our component commonality table, which are differentiated between the customer groups with the rest of the platforms remaining the same. These modules are accomplished through a longer top pillar and slider assembly, as well as a three-pronged end for the commercial kitchen, which better accommodate a wide variety of fruit and vegetable sizes, as well as stability and faster rotational speeds. However, that potentially comes at the cost of a higher risk of cuts due to a more exposed interior. In contrast, the shorter top pillar and slider assembly, as well as a single pronged end grabber, improved product packaging while still accommodating the majority of vegetables and fruits for a home kitchen, and additionally decreases the risk of cuts as the interior is more closed off and harder to access. As you can see, the interfaces between our modules remain the same between the two product models, allowing us to reuse many parts between the two product models without significant redesign. In particular, the interfaces between the linear motion shafts, the lead screw, slider supports, top plate, and lead screw end caps all remain the same, regardless of the lengths of these parts.
So here is our product family assembly diagrams. The part numbers are listed on the top here, and they correspond to the bill of materials. In the original here, the slider assembly is placed in the 8th step, and that is where differentiation occurs. And then there are 2 branches for the rest of the assembly. Then in the modified assembly, the slider assembly is not installed until around the 15th step, which then delays it about 7 steps, and then it finishes off in 2 branches until the end.